In the winter of 1918, as the guns of the Great War fell silent across the fields of Europe, another battle was just beginning. This one would be fought not in trenches, but in wind tunnels and workshops. Not with rifles, but with slide rules and blueprints. It was a war against the very laws of physics themselves, and the prize was nothing less than mastery of the sky. The propeller, that deceptively simple device of twisted wood or metal, had carried humanity into the air. Yet even as pilots pushed their machines to ever greater speeds and altitudes, they were bound by a fundamental limitation. Every propeller was a compromise, a fixed choice between contradictory demands. Optimized for takeoff, it would scream in protest at cruising altitude. Designed for speed, it would labor helplessly on the runway. The dream of flight had been realized, but flight itself remained shackled by its own mechanics. Somewhere between the noise of engines and the whisper of wind over wings, a question hung in the air. What if a propeller could think? What if it could sense the demands placed upon it and reshape itself accordingly, moment by moment, matching the will of the pilot to the resistance of the atmosphere? Most engineers dismissed this as fantasy. The mechanisms would be too complex, too heavy, too unreliable. But one man would not let go of the question. His name was Frank Walker Caldwell, and he was about to change everything. Born in 1889 in Bristol, Pennsylvania, Caldwell grew up in an era when the very concept of human flight was transitioning from impossible dream to dangerous reality. The Wright brothers had proven it could be done, but nobody yet understood why it worked or how to make it work better. Aviation was more art than science, more courage than calculation. Young Frank, however, possessed a mind that saw patterns where others saw chaos, and solutions where others saw only obstacles. He studied engineering at the Massachusetts Institute of Technology, graduating in 1912 when aviation was still in its infancy. While other engineers sought positions in established industries like railways or manufacturing, Caldwell was drawn to the sky. There was something irresistible about the challenge of flight, about taking something heavier than air and teaching it to defy gravity through nothing but shape, speed, and power. He joined the engineering staff at the Standard Aircraft Corporation and later moved to the engineering division of what would become United Aircraft and Transport Corporation. But Caldwell was not content to simply build better versions of existing designs. His mind worked differently. He saw the airplane not as a finished invention, but as a problem only partially solved. And the propeller, that essential translator of engine power into forward motion, troubled him deeply. The physics of the propeller is elegant and cruel. A propeller blade is nothing more than a rotating wing, and like any wing, it generates thrust by moving air. The angle at which the blade meets the incoming air, called the pitch, determines how much air it can move and how efficiently. A shallow pitch, like a low gear on a bicycle, allows the propeller to spin quickly and move a lot of air with each rotation. This is perfect for takeoff when the aircraft is slow and needs maximum thrust. But at high speeds, that same shallow pitch becomes a screaming liability, the blades biting into the air so aggressively that they create turbulence and waste power. A steep pitch, by contrast, is like a high gear. At cruising speed, it slices through the air smoothly, efficiently, allowing the engine to maintain speed without over-revving. But on takeoff, with the aircraft barely moving, a steep pitch is useless. The blades can't generate enough thrust to get the heavy machine rolling. The propeller stalls, the engine labors, and the aircraft remains earthbound. Every propeller in the sky was trapped in this dilemma. Pilots and engineers chose a fixed pitch that represented their best guess at an average compromise. Fighter planes used shallower pitches for quick acceleration and climb. Long-range aircraft used steeper pitches for efficient cruising. But every choice meant sacrificing performance in other flight regimes. It was like being forced to drive a car in only one gear, always. The solution was obvious. In theory, the propeller needed to change its pitch during flight, adjusting to the demands of each moment. When the pilot opened the throttle for takeoff, the blades should flatten, biting deep into the air. As the aircraft accelerated, the pitch should gradually increase, maintaining optimal efficiency. At cruising altitude, the blade should be nearly flat against the wind, turning slowly but powerfully. And if the pilot needed to dive or decelerate, the pitch should adjust again, even going fully flat to act as an air brake. In theory, it was simple. In practice, it was a nightmare. The first attempts at variable pitch propellers appeared before World War I. Crude mechanisms that allowed a pilot to manually adjust the blade angle using a lever or wheel in the cockpit. But these systems were heavy, unreliable, and dangerous. A pilot in combat or in difficult weather couldn't spare the attention to adjust propeller pitch while also managing engine controls, flight controls, navigation, and 1,000 other demands. What was needed was a propeller that adjusted itself automatically, maintaining optimal efficiency without human intervention. This was the impossible dream that haunted Frank Walker Caldwell through the 1920s. The aviation industry of that era was not kind to dreamers. The First World War had ended with warehouses full of surplus aircraft and engines, flooding the market and driving many manufacturers into bankruptcy. Airlines were small, experimental operations flying mail and a handful of brave passengers. The military had little interest in new technology after the war's staggering expenditures. Engineers who proposed expensive, complex innovations were politely shown the door. Caldwell faced skepticism from every direction. Senior engineers argued that a reliable automatic propeller was mechanically impossible. The governors and hydraulic systems needed to sense engine speed and blade loading simply couldn't be made light enough or responsive enough for aviation use. Accountants pointed out that even if such a device could be built, no airline or military would pay for it. Why invest in expensive, unproven technology when fixed-pitch propellers worked well enough?
But Caldwell had done the calculations. A truly efficient, variable pitch system wouldn't just improve performance by a few percentage points. It would revolutionize what aircraft could do. Takeoff distances would shrink dramatically, allowing operations from shorter runways. Climb rates would increase, getting aircraft to safe altitude faster. Cruising speeds would rise while fuel consumption fell, extending range and payload capacity. And in combat, the ability to rapidly adjust thrust without changing engine speed would give pilots a level of control that could mean the difference between life and death. In the silence of his workshop, Caldwell was not chasing glory. He was chasing perfection. And perfection, he was beginning to understand, required thinking about the problem in an entirely new way. The breakthrough came from abandoning human control entirely. Instead of asking a pilot to manage propeller pitch, what if the propeller managed itself based on a single parameter the pilot already controlled: engine speed? The pilot would set a desired RPM using a simple control lever. Then a governor mechanism attached to the propeller hub would continuously measure the actual engine speed. If the engine began to over-rev, the governor would increase blade pitch, loading the engine more and bringing the speed back down. If the engine bogged down, the governor would decrease pitch, unloading the engine and allowing speed to rise. The result would be a constant engine speed, automatically maintained with the propeller continuously adjusting to whatever the aircraft was doing. This was the concept of the constant speed propeller, and it was brilliant in its elegance. The pilot would no longer think about propeller pitch at all. They would simply set their desired power level, and the propeller would find the most efficient blade angle to maintain that power under any flight condition. During takeoff, the system would automatically select a shallow pitch for maximum thrust. As speed increased, the pitch would gradually steepen, keeping the engine at its optimal RPM. At cruise, the propeller would settle into an efficient configuration. And if the pilot needed to climb or accelerate, they simply increased the desired RPM and the propeller would respond instantly. But translating this concept into metal and hydraulics was a monumental challenge. The governor mechanism needed to be extraordinarily sensitive, measuring engine speed thousands of times per minute and making continuous fine adjustments to blade pitch. The hydraulic system that actually rotated the blades had to be powerful enough to overcome enormous aerodynamic forces while being precise enough for smooth, stable control. The entire system had to be light enough not to offset its own performance gains, reliable enough to trust with human lives, and simple enough to maintain in the field. Caldwell joined forces with Hamilton Standard Propeller Company, a division of United Aircraft. Hamilton Standard was one of the leading propeller manufacturers in America, with the expertise and mechanical design and manufacturing that Caldwell's vision required. Together, they began the long, difficult work of turning theory into reality. The first experimental units were disasters, governors that oscillated wildly, making the propeller hunt back and forth in search of the correct pitch. Hydraulic systems that leaked oil under the centrifugal forces of rotation. Blade retention mechanisms that couldn't handle the stress. Electric motors that added too much weight. Pneumatic systems that froze at altitude. Every promising approach revealed new problems, and every solution created new complications. Test pilots described the early prototypes as unpredictable and frightening. The propeller would surge and cycle, the blade angle changing erratically as the governor fought against aerodynamic loads it couldn't properly sense. Engine speeds would swing wildly. In some failure modes, the blades would go to full flat pitch, destroying the engine with over-revving. In others, they would go to maximum pitch and the aircraft would lose all thrust, gliding helplessly. These were not minor technical glitches. These were potentially lethal failures. But Caldwell persisted. He refined the governor design, using weighted flyweights that spun with the propeller shaft and mechanically sensed engine speed through centrifugal force. He developed better hydraulic control valves that responded more smoothly to governor commands. He redesigned the blade retention system to handle the complex combination of centrifugal, aerodynamic, and hydraulic forces acting on each blade. Slowly, through hundreds of design iterations and thousands of hours of testing, the system began to work. The key innovation was elegant simple once Caldwell found it. Instead of fighting the enormous forces trying to change blade pitch, he would use those forces. The centrifugal force of rotation naturally wanted to push the propeller blades into a flat, low-pitch configuration. By allowing this tendency and using hydraulic pressure only to increase pitch against the centrifugal force, Caldwell created a fail-safe system. If hydraulic pressure was lost for any reason, the blades would automatically return to low pitch, allowing the engine to continue running and the aircraft to maintain control. This single insight transformed a dangerous, complex mechanism into a reliable system that pilots could trust. By 1932, Hamilton Standard had a working constant-speed propeller. It was a massive, heavy unit, still far from ideal, but it worked. More importantly, it worked predictably and reliably. Test flights demonstrated performance improvements that exceeded even optimistic predictions. Takeoff distances decreased by nearly 30%. Rate of climb increased by almost 25%. Cruising speed rose while fuel consumption fell, extending range and payload capacity. And, in combat, the ability to rapidly adjust thrusts without changing engine speed would give pilots a level of control that could mean the difference between life and death. And Boeing agreed to test the constant-speed propeller on the 247. And the results silenced the doubters. The Boeing 247, equipped with constant-speed propellers, could take off in half the distance of competing aircraft. It could climb directly to cruising altitude rather than circling laboriously to gain height. It could cruise faster while burning less fuel, extending range and allowing new routes. And it could make steep, safe approaches to short runways, landing with confidence in conditions that would have grounded other airliners. Airlines began to pay attention. Then came the Douglas DC-3, and everything changed. The DC-3 was larger and more capable than the Boeing 247, designed to compete directly with it on the rapidly expanding airline routes across America. Douglas equipped the DC-3 with Hamilton Standard constant-speed propellers from the start, and the aircraft became a sensation. It was faster, more economical, and more reliable than anything else in the sky. By the mid-1930s, the DC-3 dominated American commercial aviation, and constant-speed propellers were standard equipment on virtually every modern airliner. The United States Army Air Corps took notice. Military aviation had evolved dramatically since the First World War, with faster, heavier aircraft that demanded every possible advantage. The Air Corps initiated testing of constant-speed propellers on fighters and bombers, and the performance gains were stunning. Fighter aircraft with constant-speed propellers could outclimb, outrun, and outmaneuver their fixed-pitch competitors. Bombers could carry heavier loads over longer distances with better fuel economy. In 1933, Frank Caldwell and Hamilton Standard received the Collier Trophy, aviation's highest honor for the development of the constant-speed propeller. It was recognition not just of technical achievement, but of fundamental advancement in the science of flight. The constant-speed propeller wasn't an incremental improvement. It was a redefinition of what aircraft could accomplish. Yet, even as Caldwell accepted the award, he was already focused on the next challenge. The early constant-speed propellers, while revolutionary, were complex and expensive. The governor mechanisms required precise machining and careful assembly. The hydraulic systems needed special fluids and seals. Manufacturing costs were high, and maintenance demands were significant. For commercial airlines with trained mechanics and controlled operations, this was acceptable. But if war came and military production had to scale up rapidly, the constant-speed propeller needed to become simpler, cheaper, and more rugged. Caldwell began developing what would become known as the hydromatic propeller. This new design eliminated many of the delicate components of earlier systems, replacing them with more robust alternatives that could be manufactured quickly and maintained easily. The governor became a simpler flyweight mechanism. The hydraulic system used engine oil as its working fluid, eliminating the need for separate hydraulic reservoirs and pumps. The blade retention system was redesigned for faster assembly and easier replacement in the field. The hydromatic propeller retained all the performance advantages of the original constant-speed design while becoming dramatically easier to produce and maintain. It was the ideal military propeller, and it arrived just in time. Europe was sliding toward war. Nazi Germany was rearming, building a powerful Luftwaffe with modern aircraft that threatened the peace. Britain, France, and other nations scrambled to modernize their own air forces, but they lacked badly in technology and production capacity. The United States, still officially neutral, watched with growing alarm as the storm gathered across the Atlantic. When war finally came in September 1939, the aircraft that fought in the early campaigns revealed stark technological differences. The Luftwaffe's bombers and fighters benefited from years of secret rearmament and modern design. British and French aircraft, many of them designs from the early 1930s, struggled to compete. But one advantage the Allies possessed, perhaps without fully realizing it initially, was propeller technology. German aircraft manufacturers had developed their own variable pitch propellers, primarily through companies like Vereinigte Deutsche Metallwerken and Vereinigte Leichtmetallwerken. These systems worked, but they were generally less sophisticated than American designs. Many German aircraft use electrically actuated variable pitch propellers, which were slower to respond and more prone to failure than hydraulic systems. German constant speed mechanisms were less refined, sometimes requiring more pilot intervention. The Japanese, meanwhile, relied heavily on fixed-pitch propellers throughout much of the war, or used manual variable pitch systems that demanded pilot attention at critical moments. As the war escalated and the United States entered the conflict after Pearl Harbor in December 1941, American industry faced an unprecedented challenge. The military needed tens of thousands of modern combat aircraft, all of them equipped with reliable, high-performance propellers. Hamilton Standard, working with other manufacturers like Curtiss Electric, ramped up production to levels that would have seemed impossible just years earlier. Caldwell's hydromatic propeller proved its worth under wartime conditions. The design was robust enough to be manufactured by factories full of workers with minimal training. It could be assembled quickly using mass production techniques developed in the automotive industry. And critically, it could survive combat damage and harsh operating conditions that would have destroyed more delicate systems. Propellers that took shrapnel or bullet hits often continued functioning, getting pilots home safely. Units operating from muddy forward airfields, dusty deserts, and frozen tundra found that the hydromatic propeller kept working when other systems failed. The impact on Allied aircraft performance was profound. Consider the North American P-51 Mustang, perhaps the finest fighter aircraft of World War II. The Mustang combined a revolutionary laminar flow wing with a powerful Packard Merlin engine and a Hamilton Standard hydromatic propeller. The propeller's contribution to the Mustang's legendary performance is often overlooked, but it was essential. The constant speed system allowed the Merlin engine to operate at its optimal RPM across the entire performance envelope. During takeoff, the propeller automatically selected the pitch for maximum acceleration. During climb to altitude, it continuously adjusted to maintain engine efficiency. At 30,000 feet, escorting bombers over Germany, the propeller kept the engine at peak performance. And in combat, when a pilot shoved the throttle forward for emergency power, the propeller responded instantly, adjusting pitch to absorb the increased power without allowing the engine to over-rev or lose thrust.
The same advantages apply to every American fighter that faced the Axis powers. The Republic P-47 Thunderbolt, with its massive four-bladed Hamilton Standard propeller, could climb to altitude faster than German fighters expected, ambushing them from above. The Vought F-4U Corsair, operating from aircraft carriers in the Pacific, relied on its constant speed propeller to make safe landings on pitching decks in rough seas. The Lockheed P-38 Lightning, with two engines and two propellers that had to be carefully synchronized, used constant speed systems to automatically maintain matched power between the engines, eliminating the asymmetric thrust problems that plagued earlier twin-engine fighters. British aircraft also benefited from American propeller technology. Many Supermarine Spitfires and Hawker Hurricanes were retrofitted with constant speed propellers as the systems became available, significantly improving their performance against the Luftwaffe. The difference was particularly noticeable in climb rate and high-altitude performance, where the constant speed propeller allowed British fighters to more effectively intercept German bombers. In the great bomber fleets that carried the war to Germany and Japan, constant speed propellers were equally crucial. The Boeing B-17 Flying Fortress used four Hamilton Standard hydromatic propellers, each one automatically managing its engine for optimal efficiency. On missions that lasted 8 hours or more, flying deep into enemy territory and back, fuel efficiency was the difference between completing the mission and going down in the channel. The propellers continuously adjusted to maintain efficient cruise, stretching every gallon of fuel to its maximum range. The consolidated B-24 Liberator, produced in greater numbers than any other American military aircraft, relied on the same technology. The B-24's long, high aspect ratio wing made it exceptionally sensitive to power management. Constant speed propellers allowed pilots to maintain precise control of all four engines, keeping the aircraft stable and efficient through long flights over the Atlantic or Pacific. During critical air campaigns, the advantages multiplied. In the Battle of Britain, when the Royal Air Force held the line against overwhelming German numbers, every percentage point of performance mattered. Spitfires and Hurricanes equipped with constant speed propellers could climb faster to intercept incoming bombers, could sustain combat at altitude longer, and could safely return to base with lower fuel reserves. These small margins accumulated across hundreds of engagements, helping swing the battle toward British victory. In the great bomber fleets that carried the war to Germany and Japan, constant speed propellers were equally crucial. During the Battle of Britain, when the Royal Air Force held the line against overwhelming German numbers,
every percentage point of performance mattered. Spitfires and Hurricanes equipped with constant speed propellers could climb faster to intercept incoming bombers, could sustain combat at altitude longer, and could safely return to base with lower fuel reserves. These small margins accumulated across hundreds of engagements, helping swing the battle toward British victory. In the air war over Europe, when American heavy bombers fought their way through clouds of German fighters to strike industrial targets, the escort fighters' performance was absolutely critical. P-51 Mustangs and P-47 Thunderbolts had to climb to meet the bombers, cruise at their altitude for hours, maintain combat readiness throughout the mission, then still have enough fuel to fight their way home. Without constant speed propellers automatically optimizing every phase of the flight, these escort missions would have been impossible. The long-range penetration raids that broke the Luftwaffe's back depended on technology that Frank Caldwell had conceived 2 decades earlier in a workshop in Connecticut. In the Pacific Theater, where distances were measured in thousands of miles and every mission stretched the limits of aircraft range, propeller efficiency became a matter of life and death. American fighters operating from island bases had to reach enemy formations far from home, fight, and return. Bombers striking targets across vast ocean expanses couldn't afford to waste fuel. The constant speed propeller's ability to maintain optimal efficiency at every engine setting translated directly into mission success and pilot survival. Manufacturing challenges during wartime were immense. Hamilton Standard's factories ran around the clock, producing propellers by the thousands. The company trained new workers in weeks to perform tasks that had previously required months of apprenticeship. Quality control became a critical concern. A defective propeller could kill a crew and lose an aircraft. Engineers like Caldwell moved between the design offices and the factory floor, identifying production problems and developing solutions that could be implemented immediately. Material shortages forced innovation. Critical components that had used strategic materials like chromium or tungsten had to be redesigned to use more common alloys. Some parts that had been machined from solid billets were redesigned to be forged or cast, saving metal and reducing machining time. Sealed designs evolved to work with available rubber compounds when preferred materials became scarce. Every change had to maintain reliability while improving manufacturability.
Field maintenance was another constant concern. Propellers operating in combat zones couldn't be sent back to factories for service. They had to be maintained, adjusted, and repaired by mechanics working in tents, in mud, in snow, under fire. Caldwell's team designed special tools and wrote simplified maintenance procedures that allowed field crews to service the hydromatic propellers with minimal training and limited resources. This attention to operational reality, this understanding that brilliant engineering meant nothing if it couldn't be maintained in a foxhole, made the constant speed propeller a true weapon of war. As the war progressed, incremental improvements continued. Blade designs became more efficient, using advanced airfoil sections developed through wind tunnel testing. Anti-icing systems were integrated to prevent ice formation at altitude. Governors were refined for even smoother response. Hydraulic systems became more resistant to contamination and temperature extremes. Each improvement represented countless hours of development work, testing, and production engineering. The German and Japanese response to Allied propeller technology reveals the importance of this seemingly mundane component. Late in the war, German engineers developed increasingly sophisticated variable pitch propellers, trying to match American performance. But they were playing catch-up, implementing technology that the Allies had already perfected and were producing by the tens of thousands. Japanese manufacturers, working with limited resources and facing strategic bombing, struggled to produce even basic variable pitch propellers in adequate numbers. Many Japanese fighters and bombers through 1944 and 1945 still used fixed pitch or manual variable pitch propellers, accepting performance penalties that contributed to their growing disadvantage in the air war. The cumulative effect of propeller technology on the air war is difficult to quantify precisely, but it was undoubtedly significant. If we imagine an alternate history, where Allied aircraft used fixed-pitch propellers while Axis aircraft had constant-speed systems, the outcome of many air battles would have reversed. The margins were often that narrow. An aircraft that climbs slightly faster intercepts the enemy at an advantage. An aircraft with slightly longer range completes missions that would otherwise be impossible. An aircraft that responds slightly quicker in combat maneuvers inside its opponent's turn. These small differences, multiplied across thousands of aircraft and millions of flight hours, shape the war. Frank Caldwell never sought the spotlight. While test pilots became celebrities and aircraft designers achieved fame, Caldwell remained focused on the technical work. He continued developing improved propeller systems throughout the war, but his name rarely appeared in newspapers or newsreels. He was not a general, or a politician, or a hero in the traditional sense. He was an engineer who had solved a problem, and in solving it, had changed the world. Yet his contribution to Allied victory was immeasurable. Every bomber that reached its target and returned home flew on propellers that embodied Caldwell's vision. Every fighter that climbed to altitude and engaged the enemy benefited from technology he had pioneered. Every transport aircraft that carried supplies to forward bases, every patrol plane that hunted submarines, every trainer that prepared new pilots, all of them relied on constant-speed propellers to achieve performance that would have been impossible a generation earlier. The constant-speed propeller transformed aviation physics in a fundamental way. Before Caldwell's invention, engine power and propeller thrust were loosely coupled, with the pilot manually managing both. After, they became a unified system, with the propeller automatically translating power into thrust under any condition. This freed pilots to focus on flying and fighting rather than managing mechanical details. It allowed engines to operate at their most efficient speeds regardless of flight conditions. It extracted maximum performance from every horsepower, every gallon of fuel, every minute of flight time. In the broader context of wartime technology, the constant-speed propeller represents something profound about innovation under pressure. It wasn't a weapon, though it made weapons more effective. It wasn't armor, though it helped protect aircrews by improving aircraft performance and reliability. It was pure efficiency, a mechanism that made every other system work better. In a war where production capacity and resource management were critical strategic factors, efficiency was its own form of weapon. The development of the constant-speed propeller also illustrates the importance of solving problems thoroughly rather than quickly. Caldwell could have settled for early prototypes that worked marginally well, rushing them into production to capitalize on the commercial opportunities of the 1930s. Instead, he insisted on refining the system until it was truly reliable, truly efficient, truly worthy of trust. That patience, that perfectionism, meant that when war came and reliability mattered more than ever, the technology was ready. After the war ended, constant-speed propellers remained standard equipment on virtually every aircraft with a piston engine. The commercial aviation boom of the late 1940s and 1950s relied on transport aircraft like the Douglas DC-6 and Lockheed Constellation, all equipped with advanced hydromatic propellers. Military aviation continued using the technology on aircraft like the Boeing B-29 Superfortress and later piston-powered aircraft. Even as jet engines began to dominate military aviation, propeller aircraft remained essential for transport, patrol, and specialized roles, and all of them used constant-speed propellers to achieve performance that would have been impossible a generation earlier.
Frank Caldwell continued working in aviation engineering for many years after World War II, contributing to turboprop development and other advanced propulsion systems. He died in 1975, having witnessed aviation evolve from wood and fabric biplanes to supersonic jets and space rockets. But his most important contribution remained the constant-speed propeller, the device that had made modern aviation possible and helped win the most consequential war in human history. Standing now in the 21st century, when jet engines power nearly all military and commercial aircraft, it's easy to overlook the propeller's role in shaping history. We live in a world the Allied victory created, where democratic values and individual freedom prevailed over fascism and militarism. That victory was built on countless factors: industrial production, strategic decisions, the courage of millions of soldiers, sailors, and airmen. But it was also built on technology, on innovations that gave the Allies critical advantages in combat. The constant-speed propeller was one of those innovations. Not the largest or most obvious, not the one that fills museum exhibits or documentary films, yet essential, absolutely essential to Allied air superiority. Every percentage point of performance improvement it provided multiplied across every aircraft, every mission, every day of the war. Those incremental advantages accumulated into strategic superiority. Think of a P-51 Mustang climbing through cold European sky, escorting bombers toward Germany. The pilot advances the throttle, the Merlin engine roars, and the aircraft surges upward. Behind him, unseen and unconsidered, the hydromatic propeller adjusts its pitch moment by moment, maintaining perfect efficiency as altitude increases and air thins. The pilot doesn't think about blade angle or engine loading or aerodynamic forces. He thinks about formation position, about navigation, about watching for enemy fighters. The propeller handles itself, precisely as Caldwell intended. That seamless integration of human and machine, that translation of intent into action without conscious effort, represents the highest achievement of engineering. The technology disappears, becoming invisible, allowing the human operator to focus on the mission rather than the mechanism. In combat, when attention is survival and distraction is death, this matters absolutely. Or think of a B-17 over the North Sea, engines laboring to maintain altitude with battle damage and fuel running low. The pilots nurse the throttles, coaxing maximum range from remaining fuel. Below them, icy water waits. Behind them, the English coast remains distant. Everything depends on efficiency, on extracting every possible mile from every gallon of avgas. The constant-speed propeller sensing engine load and adjusting blade pitch constantly stretch that fuel as far as physics allows. When the bomber finally crosses the coast and makes an emergency landing at the first available airfield, the crew owes their survival to many things, but among them, certainly, is a propeller system that never quit optimizing, never stopped working for their survival. These stories repeated thousands of times throughout the war. Pilots who never knew Frank Caldwell's name flew home safely because his invention gave them the performance margin they needed. Missions succeeded because aircraft could fly farther, climb higher, respond quicker. The vast air campaign that broke Axis power and brought the war to an end relied fundamentally on Allied control of the skies, and that control depended on technological superiority in countless areas. The constant-speed propeller was one thread in that tapestry, but pull that thread, and the whole fabric weakens. In the quieter moments of history, between the dramatic battles and political turning points, engineers like Caldwell work on problems that most people never consider. How do you make an aircraft more efficient? How do you automate a control system? How do you build something that works reliably under conditions that destroy other mechanisms? These are not questions that make headlines, but they are questions that change possibilities. Caldwell's answer to the propeller problem was elegant in the way that great engineering is always elegant. It worked with nature rather than against it, using centrifugal force instead of fighting it. It simplified the pilot's task rather than complicating it. It failed safely, returning to a workable configuration rather than catastrophically breaking. And it could be manufactured at scale, maintained in the field, and trusted in combat. These qualities distinguish truly practical innovation from clever theory. The extension extends beyond propellers or aviation or even engineering. In any complex challenge, the solution that works is rarely the most elaborate or intellectually impressive. It is the solution that addresses real constraints: manufacturing, maintenance, human factors, failure modes, cost, reliability. It is the solution that makes the difficult look easy, that hides complexity behind simplicity, that just works when everything depends on it working. Frank Caldwell understood this intuitively. His constant-speed propeller was not the most complex mechanism he could have designed. It was the simplest mechanism that could reliably solve the problem. That discipline, that restraint, that focus on practical functionality over theoretical perfection made his invention successful when more elaborate approaches failed. As we consider the sweep of World War II and the technology that shaped it, we tend to focus on the dramatic innovations. Radar, which saw through darkness and clouds, the atomic bomb, which ended the war in a flash of terrible light, encrypted communications, which protected strategic decisions. These were transformative technologies that clearly and obviously changed the war's course. But wars are also won by less dramatic innovations, by incremental improvements that accumulate into decisive advantages. Better propellers, more reliable engines, improved fuel formulations, stronger aluminum alloys, and more efficient manufacturing processes. None of these individually determined the war's outcome. Together, they created the foundation for Allied victory. The constant-speed propeller sits in that category of essential yet overlooked innovations. It made every Allied aircraft better without requiring major redesign. It improved performance across every flight regime without demanding new pilot training. It enhanced reliability while reducing maintenance burden. It was the rare innovation that offered advantages without significant trade-offs, that made everything else work better simply by existing.
In the museums where World War II aircraft are preserved, beautifully restored and gleaming under careful lighting, the propellers often receive little attention. Visitors photograph the nose art, admire the cockpit, marvel at the gun positions. The propeller is just there, a necessary component, its sophistication hidden. Yet that propeller represents countless hours of development work, thousands of design iterations, the accumulated expertise of an entire engineering team. It represents Frank Caldwell's vision made real, his impossible dream transformed into mundane reliability. Perhaps that is the ultimate success of engineering, to become invisible, to work so reliably that no one thinks about it anymore. The constant-speed propeller achieved that success. It became standard, expected, assumed. Pilots trusted it completely. Mechanics serviced it routinely. Engineers built it into every new aircraft design without question. The revolution Caldwell started became the established norm so quickly that people forgot there had ever been another way. And yet, if we look back at those critical years when democracy hung in the balance and the outcome of the war remained uncertain, we can see the propeller's role clearly. We can see how it contributed to Allied air superiority, how it enabled the missions that mattered, how it brought pilots home safely. We can see, if we look carefully enough, how one engineer's pursuit of efficiency changed the trajectory of history. The Allies won World War II for many reasons. They had greater industrial capacity. They made better strategic decisions. They developed superior technology across many domains. They benefited from the courage and sacrifice of millions who fought and died to preserve freedom. No single innovation or individual determined the outcome. Victory emerged from the combination of countless factors, each contributing its part. But among those countless factors, the constant-speed propeller deserves recognition. It made Allied aircraft better. It made Allied pilots more effective. It made Allied air power decisive. And in doing so, it helped secure the victory that shaped the world we inhabit today. Frank Caldwell never commanded armies or led nations. He never flew combat missions or made strategic decisions that altered the war's course. He was an engineer who solved the problem, who saw what was impossible and made it real. In the silence of his workshop, surrounded by drawings and prototypes and the quiet hum of testing equipment, he changed aviation forever. That is the nature of true innovation. It happens in workshops and laboratories, in the patient work of individuals who refuse to accept the impossible, who see solutions where others see only obstacles.
It happens when someone asks a simple question and pursues the answer with relentless determination, through failure and doubt and skepticism, until the answer emerges. The constant speed propeller reminds us that victory in war, like progress in peace, depends not only on grand strategies and heroic sacrifices, but also on the quiet work of engineers who make things work better. It depends on individuals who see a problem that everyone else has learned to live with and who refuse to accept that compromise. It depends on the patience to refine an idea through hundreds of iterations, the discipline to demand reliability over cleverness, and the vision to see how one small improvement can cascade into transformative change. In the end, Frank Caldwell's greatest achievement was not the awards he received or the recognition he earned. It was the countless pilots who returned home safely because their aircraft performed just a little bit better. It was the missions that succeeded because fuel stretched just a little bit farther. It was the strategic advantage that accumulated, flight by flight, mission by mission, until Allied air power became overwhelming and decisive. The propeller that won the war was not a weapon. It was efficiency made mechanical, physics made practical, innovation made invisible. It was the product of one engineer's refusal to accept the impossible and his determination to make flight itself more perfect. And in that pursuit of perfection, pursued with patience and discipline through years of development and refinement, Frank Caldwell helped change the course of history. The sky remembers, even if we forget. Every aircraft that has flown since, every advancement in aviation that followed, builds on the foundation Caldwell laid. The principle he proved, that machines can adapt themselves automatically to optimize performance, has echoed through decades of aerospace engineering. From variable geometry wings to digital engine controls, from adaptive flight systems to autonomous aircraft, the thread of his innovation runs through the entire evolution of flight. But perhaps the deepest lesson of Frank Caldwell's story is simpler and more human. It is that individual effort matters, that one person working with dedication and vision on a problem that others dismiss can change the world. That engineering is not merely calculation and design, but a form of service, a way of using human intelligence to extend human capability and protect human life. Somewhere over the Atlantic, on a cold morning in 1943, a young American pilot flew his P-51 Mustang toward Europe. He was 22 years old, fresh from training, flying his first combat mission. His hands gripped the controls nervously. His eyes scanned the sky for enemy fighters. His mind raced with fear and duty and determination. Behind him, Hamilton's standard constant-speed propeller blades rotated smoothly, their pitch adjusting moment by moment, maintaining optimal efficiency as the aircraft climbed toward altitude. The pilot never thought about the propeller. It simply worked, perfectly and invisibly, just as it was designed to do. That young pilot survived the war. He returned home, married, raised a family, lived a long and peaceful life. He flew dozens of combat missions, survived encounters with enemy fighters, navigated through storms and mechanical failures and all the chaos of war. In his later years, when people asked him about his service, he spoke of friends lost and battles won, a fear overcome and duty fulfilled. He never mentioned the propeller. But the propeller was there. Every flight, every mission, every moment his life hung in the balance. It was there in the quiet competence of engineering done right, in the invisible reliability of a system that simply worked. It was there in Frank Caldwell's vision translated into metal and hydraulics and precision manufacturing, serving its purpose without glory or recognition.
That is how great engineering serves humanity, not through spectacle or drama, but through quiet excellence. Not through fame or recognition, but through function and reliability. Not by being noticed, but by being so good that it becomes invisible, so reliable that it becomes expected, so essential that we cannot imagine how we ever lived without it. The constant speed propeller changed aviation.
It helped win World War II. It enabled the modern world to emerge from the darkness of that conflict. And it did all of this through the determined vision of one engineer who refused to accept that the impossible could not be made real. In workshops and laboratories across the world today, engineers work on problems that will shape tomorrow. They pursue efficiency, reliability, and performance with the same dedication Caldwell brought to his work decades ago. Most of them will never be famous. Most of their innovations will become invisible, assumed, expected. But some of them, perhaps, will change the world as profoundly as the constant-speed propeller changed aviation. This is the heritage Frank Caldwell left behind. Not merely a device or a patent or a trophy, but a demonstration of what individual vision and persistent effort can accomplish. In a time when the world faced its darkest hour, when tyranny threatened to extinguish freedom and hope seemed fragile, an engineer in Connecticut solved the problem about propeller efficiency. And in solving that problem, he helped ensure that the forces of democracy and freedom would prevail. The propeller spins on, a testament to human ingenuity and the power of ideas made real. Each rotation is a reminder that great achievements often emerge from quiet persistence, that world-changing innovation can come from addressing seemingly mundane problems with extraordinary dedication, and that the work of engineers, invisible though it may be, shapes the trajectory of human history. Frank Walker Caldwell understood the physics of flight, but he understood something deeper as well. He understood that perfection is worth pursuing even when others call it impossible, that reliability matters more than brilliance, and that true innovation serves those who will never know its creator's name. In pursuit of that understanding, he created something that changed aviation forever and helped secure the freedom of the world. The sky above us is filled with his legacy. Every flight that takes off, every journey completed, every life carried safely to its destination, all of them echo the work Caldwell began nearly a century ago. The propeller that won the war continues to serve, adapted and refined, but fundamentally unchanged, a silent partner in humanity's endless quest to transcend the bounds of Earth and touch the realm of air. This is how one engineer changed the world, not with thunder and lightning, but with patience and precision, not with grand gestures, but with careful refinement, not seeking glory, but pursuing perfection. And in that pursuit, in those quiet hours of testing and calculation and incremental improvement, Frank Caldwell created something far greater than a mechanism. He created possibility itself, the possibility that aircraft could be more efficient, that pilots could be safer, that Allied forces could control the skies and freedom could prevail. The story of the constant-speed propeller is ultimately a story about human potential. It is about what becomes possible when vision meets discipline, when innovation serves necessity, when engineering excellence solves real problems for real people in real danger. It is about the difference between accepting limitations and transcending them, between living with compromise and demanding perfection. And it is about Frank Caldwell, an engineer who looked at a propeller and saw not what it was, but what it could become, who refused to accept that the dream of automatic efficiency was impossible, who worked through failure and skepticism and technical challenges that would have defeated lesser engineers, who created something so good that it became invisible, so reliable that it became expected, so essential that it helped change the course of history. In the end, that is the measure of true innovation, not fame or recognition or awards, though Caldwell received all of those, but impact, service, the quiet satisfaction of knowing that your work mattered, that your vision became reality, that somewhere in the vast sweep of human history, your contribution helped tip the balance toward light rather than darkness. The propeller that won the war continues to spin, a testament to one engineer's refusal to accept the impossible and his determination to make flight itself more perfect. and in its endless rotation, in its automatic adjustment from takeoff to cruise to landing, in its reliable service through peace and war and all the decades that have followed, we find a reminder of what human ingenuity can accomplish when vision meets dedication. Frank Caldwell gave the world a better propeller, but more than that, he gave the world a demonstration of what becomes possible when we refuse to accept limitations, when we pursue excellence with patience and discipline, when we dedicate ourselves to solving real problems with innovative solutions. That gift extends far beyond aviation, far beyond World War II, reaching across all the years that have passed and all the years yet to come. The constant speed propeller changed aviation. It helped win the war. It saved countless lives. It enabled the modern world to emerge from conflict and build the peaceful, prosperous global civilization we now inhabit. And it did all of this because one engineer, working in a workshop in Connecticut, refused to accept that the impossible could not be made real. That is the power of innovation. That is the legacy of Frank W. Caldwell. And that is how one man's pursuit of perfection helped change the world forever.